Today we are going to see some more examples of consistency. So we have seen the sufficient condition for consistency is sufficient condition for consistency is the condition first is expected value of Tn is equal to theta. That is bias of Tn theta tends to 0 as n tends to infinity. As n tends to infinity. It means if Tn is unbiased for theta, then there is no problem. If it is biased, then bias should be tends to 0 as n tends to infinity. And second condition is that variance of Tn is equal to variance of Tn tends to 0 as n tends to infinity. If these both conditions get satisfied, then we can say Tn is a consistent estimator of theta. Tn is a consistent estimator of theta. But if these conditions get not satisfied, then we cannot say about consistency of estimator Tn. That is, another way is not converse is not true. If these conditions are not satisfied, then we cannot say that estimator is consistent or not. So this is one of the most important condition that we have to need to take into account. That is, if both conditions are satisfied, estimator is consistent. If one of the condition is not satisfied, then we cannot say about consistency of estimator. Then we have to prove using definition. For example, suppose x1, x2, xn be a random sample from normal mu1, and suppose our Tn is xn, that is nth ordered, that is nth observation is our xn. Then we have to check its consistency. So expected value of xn is equal to mu, and variance of xn is equal to 1, since this follows normal distribution. So expected value of xn is equal to mu, first condition gets satisfied, but second condition, variance of xn is equal to 1, this does not tends to 0 as n tends to infinity. So here we cannot say about whether xn is consistent or not. To check its consistency, if these conditions get unsatisfied, we have to go to the definition. And what is our definition? Probability of mod Tn minus theta. Mod Tn minus theta is less than epsilon. Should tends to 0 as n tends to infinity. This is our definition. So now we will take probability of xn minus mu less than epsilon. Consider this probability. So this will be less than minus epsilon to plus epsilon. Xn minus mu will lies between minus epsilon to plus epsilon. So probability of minus epsilon, this is a standard normal. Since we have subtracted its mean and divided by 1, so it is standard normal less than epsilon. So what is this probability? So which is equal to integration minus epsilon to plus epsilon phi z dz, where phi z is a PDF of standard normal distribution, and this does not tends to 1. So xn is a not consistent estimator of mu. So here we can see that one of the condition is not satisfied. Then to check consistency of estimator, we have to use the original definition, and by using definition we have this here. That is a definition is probability Tn is said to be consistent estimator of theta if probability of absolute value of Tn minus theta less than or equal to epsilon, this tends to 1, or this greater than or epsilon, this tends to 0 as n tends to infinity. So in this way we have to use these conditions carefully. Now we will go to example. Suppose x1, x2, xn be a random sample from Python lambda. Then we have to check consistency of estimators. The first estimator is x bar. Second estimator is x1 minus x2 bracket square divided by 12. Third estimator is nx bar upon n plus 1. Fourth estimator is x1 plus x2 divided by 2, and last estimator is 2 times summation ixi divided by n upon n into n plus 1. So we have to check consistency of these estimator. We know, first we will consider these two estimators. So let T1 is equal to x1 minus x2 bracket square divided by 12. So x1 minus x2 square is x1 square minus 2x1 x2 plus x2 square divided by 2. So here we can take expectation of T1. Expectation of T1 is expectation of this term, and expectation of this term is 1 by 2 expected value of x1 square minus 2 expected value of x1 into expected value of x2 plus expected value of x2 square. Since these are independent, so expectation can be written as product of their expectations. So this is a random sample. Now we know that variance of xi is lambda and expected value of xi is lambda. So expected value of xi square is lambda minus lambda square. Since variance of xi is formula is expected value of xi minus expected value of xi bracket square. So this comes out to be variance of xi plus expected value of xi bracket square. So lambda plus lambda square. So now we will put it here. So expected value of T1 is equal to 1 by 2 lambda plus lambda square minus 2 lambda square. Expectation of x1 and x2 is lambda plus lambda square plus lambda. So what we have 1 by 2. So lambda square plus lambda square minus 2 lambda square get cancelled. So it is 2 lambda, and which is equal to lambda. So T1 is unbiased estimator of lambda. So T1 is unbiased estimator of lambda, and here we can see the x1 plus x2 by 2, x1 minus x2 bracket square by 2. This does not contain n terms. Since consistency is large sample property, consistency is a large sample property. So as it does not contain any nth term, so these will be not consistent estimators because their sampling distribution does not contain any nth, does not depend on sample of size n. So this is not consistent estimator. Similarly, in this case also, in case of x2, T2, x1 plus x2 by 2. So this is also equal to expectation of this term is equal to lambda plus lambda divided by 2, and it is equal to lambda. It is also unbiased estimator of lambda, but this will be not consistent estimator. This will not consistent estimator since sampling distribution of T2, does not depend on n, doesn't depend on n, as well as sampling distribution of, we have seen x1 minus x2 bracket square divided by 2. Its sampling distribution is also not depending on n. So this will be not a consistent. There is no point to check consistency of these estimators since consistency is a large sample property. So these are not consistent estimators. So now we'll check expected value of, now we will check x bar. So consider T3 as expected value of x bar. So expected value of summation xi by n, which is equal to summation of expected value of xi divided by n, and this is equal to n lambda divided by n, so it is equal to lambda. So variance of x bar is equal to, we know that variance of xi is equal to variance of summation xi upon n, 1 upon n square into summation of variance of xi, and which is equal to n sigma square divided by n square, which is equal to sigma square upon n. So variance of x bar, this tends to 0 as n tends to infinity, and it is unbiased estimator, so bias is already 0. So variance expectation is this, and variance tends to 0, so this is a consistent estimator. So x bar is a consistent estimator of lambda. Now we will check about consistency of n into n plus 1. We have noted that if Tn is consistent estimator of theta, then an Tn plus Bn is consistent estimator of theta provided an tends to 1 and Bn tends to 0 as n tends to infinity. So by using this, consider, by using above result, we know that x bar is a consistent estimator of lambda. X bar is a consistent estimator of lambda. So consider n upon n plus 1 as an and x bar as a Tn. So x bar n. So n upon n plus 1 can be written as, n upon n plus 1 can be written as 1 upon 1 plus n. So this is an. So as n tends to infinity, an tends to 1. So an Tn, so therefore an Tn, that is n upon n plus 1 into x bar n is a consistent estimator of lambda. So we have used this theorem and we have proved this is consistent estimator. Now we will consider another estimator, that is T5 summation I xi upon n plus 1 into 2 times. So we will check its consistency. So expected value of T5, so this is equal to 2 upon n into n plus 1. So summation of expected value of Ixi, so 2 upon n plus 1. So summation of I into expected value of xi, so 2 upon n plus 1. So summation I into expected value of xi is lambda. So we can take 2 lambda upon n plus 1, summation I, and I is running from 1 to n. So this is nothing but a sum of first n natural numbers, and we have got what we have, n into n plus 1 by 2. So this is equal to lambda. So this is unbiased estimator. So our first condition of sufficiency is proved. Now we will check its variance. So what is its variance? So variance of T5 is equal to 2 times. So variance of 2 upon n plus 1 into summation Ixi. So 4 upon n square into n plus 1 bracket square into variance of summation Ixi. So which is equal to 4 upon n square upon n plus 1 bracket square into summation of variance of Ixi, and which is nothing but 4 upon n square into n plus 1 bracket square into summation of I square into variance of xi. So which is equal to 4 upon n square into n plus 1 bracket square. So summation I square, and variance of xi is lambda. So 4 lambda into summation I square. So first n natural number, sum of squares of first n natural number is n into n plus 1 into 2n plus 1 divided by 6. So n plus 1 bracket square here. So 4, so it is 2 by 3 lambda into, so n get cancelled, so lambda upon n divided by n plus 1 into 2n plus 1. So this can be written as, 2 by 3 lambda 2 plus 1 upon n divided by n, and this is divided by n plus 1. So this tends to 0 as n tends to infinity. So this is tending to 0 as n tends to infinity. So first condition is get satisfied, that is it is unbiased and its variance tends to 0 as n tends to infinity. So this is also a consistent estimator. So this is another example of consistent estimator.